Now, we've already looked at taking a binomial distribution and approximating it by a normal distribution. We've also looked at taking a binomial distribution and approximating it by a Poisson distribution. And this video is about taking a Poisson distribution and approximating that by a normal distribution. It's worth bearing in mind that Poisson and binomial are discrete distributions, and a normal distribution is a continuous distribution, so numbers can take any value. So this means that when we're going from binomial to normal or Poisson to normal, we need to make a continuity correction. Now, you'll remember that in a Poisson distribution, the mean is lambda and the variance is lambda. So when we're using a normal approximation to a Poisson distribution, the parameters for the normal distribution are going to be lambda lambda. So when using a normal approximation to a Poisson distribution, p lambda can be approximated by a normal distribution, mean lambda, variance lambda. So let's consider this problem here. We've got a Poisson distribution with parameter 12, x is discrete, and we're going to approximate this by using a normal distribution, mean 12, variance 12. Y is continuous. The normal distribution is continuous, a Poisson and a binomial are discrete. So why is it wrong to say the probability that x is 14 is approximately the probability that y is 14? Well, let's think about this. The probability that y is 14. Y is a normal distribution with mean 12 and variance 12. What's the probability that y is 14? 12 is here, 14 is here. So the probability that y is 14 is the area of that line. Now that doesn't make any sense. You can't have an area of a line. Remember, in a normal distribution, the probabilities are worked out by areas, so we need to make this continuity correction, and we need to consider the bits either side, where that number there is 13.5, that number there is 14.5. So this whole area here, between 13.5 and 14.5, is the probability that y is 14. So what we need to do is to say the probability that x is 14 is approximately equal to the probability that y is between 13.5 and 14.5. So when is it appropriate to use a normal approximation to a Poisson? Let's have a look at this diagram here. This shows in the red bars the Poisson distribution, that's discrete, and the parameter here is 12. And the line, the black line that goes like that, represents the normal distribution with mean 12 and variance 12. And you can see that they are fairly similar. So when the parameter is 12, then it's perfectly okay to use a normal approximation. Here we've got a Poisson distribution with parameter 3. The red bars show the Poisson distribution, and then the black line shows the normal distribution, and you can see here that it's not a particularly good fit. So when the parameter is 3, it's not appropriate to take a normal approximation. So the rule is, when lambda is greater than 10, it's okay to use the normal approximation. So here we have an example. X has a Poisson distribution with parameter 85, and we want to find the probability that x is greater than 80. So let's have the full working. X has a Poisson distribution parameter 85, so y has a normal distribution with mean 85 and variance 85. We want the probability that x is greater than 80. So let's think about this. 79, 80, 81. We want x to be greater than 80, not including 80. So what we're looking at with our continuity correction is that y is greater than 80.5. So let's write this down. Probability that y is greater than or equal to 80.5. And that's the probability that z is greater than 80.5 minus 85 minus the mean over the standard deviation. That works out to be minus 0.49. And by the normal rules of the normal distribution, that's z to be less than plus 0.49, which is 0.6879. And finally, just to reiterate that the continuity correction is always going to be used when we're going from a discrete distribution to a continuous distribution. So if we're going from binomial or we're going from Poisson to a normal, if we're going to the normal, we always need this continuity correction.